All right, so this is video 3, okay? Video 3 for Friday, all right? So we've talked about the fact that there are two factors involved in a spontaneous process, both enthalpy and entropy, right? Enthalpy is the most important. If it's exothermic, then it should be spontaneous, right? If it's endothermic, then you need an increase of entropy to make it spontaneous. But here's the deal. Entropy is dependent upon temperature, and there are situations in which the at really high temperatures, entropy can actually flip the sign of delta H, which is crazy but true, right? So what that means then is that we can't use just one to determine the spontaneity of a system. We need to know delta H and delta S, and we need to be able to relate them to one another. That's the problem. So, yay America, because this does not happen very often, but we actually have an American mathematician who solved this problem. An American mathematician is the one who relates delta H, change in enthalpy, to delta S, change in entropy. He's a guy by the name of Gibbs, okay? And we call this, he basically comes up with a new thermodynamic constant, which the symbol for this is G for his name. But a lot of times people just refer to delta G as change in free energy, or maybe they call it change in Gibbs free energy. Sometimes they use this name, sometimes they don't. But G is equal to H minus TS. Although, let's be honest, we care about delta G, right? So delta G is equal to, so the change in free energy is equal to delta H, the change in enthalpy, minus T, notice not delta T. Why? Because we are not talking about situations in which temperature changes. We are talking about isothermal processes, right? Isothermal. So just T times delta S, change in entropy. So delta G equals delta H minus T delta S. You should know that equation. That is a huge equation. You should memorize it. Add it to your list of things that you memorize. Okay? All right, so basically, where is delta G coming from? Well, these equations should look familiar to you because we just talked about them in the last video, right? So delta S surrounding is equal to negative Q over T. And we know that a lot of times we can get Q from delta H. And we know that delta S universe is equal to delta S system plus delta S surroundings. So, but we want to relate the universe to only one of the two. So we can replace surroundings with something that relates to system to get everybody onto one plane wave. Don't worry about following through all this. I'm just talking you through it. You don't have to memorize any of this or be able to duplicate it. If we then take this and we multiply both sides by negative T, take a look at what this is. It becomes delta H minus T delta S, which is exactly what delta G equals. So what does that mean? That means that delta G at constant temperature and pressure is equal to the negative temperature times delta S universe. So what does this mean? I can study the system and the surroundings at the same time without actually studying the system and the surroundings. Okay, so let's talk about what the signs of delta G correspond to. All right, so delta G can either be negative, positive, or zero, right? If delta G is negative, that means it is spontaneous in the forward direction, okay? Moving from reactants to products. If delta G is zero, then that means it's not spontaneous in any direction. It is at equilibrium. This is not proceeding in any direction. And if delta G is positive, that means it's non-spontaneous in the forward direction. But remember, the opposite of spontaneous is non-spontaneous. So if delta G is positive, it's non-spontaneous in the forward, but it would be spontaneous in the reverse, right? So we love delta G. We love delta G in the field of thermo because it allows us to look at one person's perspective. It means that we can keep just looking at the system's perspective and basically like say screw you to the surroundings and move on, right? Because since delta G relates to delta S universe, that accounts for the surroundings, so we don't have to on our own account for the surroundings, right? So it's nice. It saves us a little bit of work. Okay. Now, so in this example, it says calculate delta G in kilojoules and determine if it is spontaneous. Okay. So in this example, I'm going to shoot past this because I'm going to work these examples in the next video. All right. And so I'm just going to skip it for now. All right. So moving forward, so we'll go back. That was slide 46. We'll go back in the next video. So as chemists, right, we're interested in chemical reactions that don't always have to occur at 25 degrees Celsius, all right? Sometimes they do, sometimes they don't. But what we see here is that free energy is dependent upon the temperature because entropy is dependent upon the temperature and free energy is dependent upon entropy, right? So basically when it comes down to it, this equation, delta H minus T delta S, you have two terms. You have the enthalpy term, which could be negative or positive, and you have the entropy term that could be negative or positive. I mean, temperatures are always positive, but delta S can be positive or negative, and since it's negative T delta S, when delta S is negative, the entropy term becomes positive. And when delta S is positive, the entropy term stays as negative. So there's definitely a dependence between delta G and its effect on entropy and the temperature. But I also want you to think about what this means as far as when delta G is dependent upon temperature. So we need to talk about what is favorable and what normally refers to spontaneity from each enthalpy and entropy's perspective. Okay, and the easiest way for me to do this is to work this out on a sheet of paper with you. So I am going to kill this video and then I'm going to do one from my phone that works the example we just shot past and works this out for you on a piece of paper because I think it will help you. All right, so into video 3, I'll see you in video 4.